Video lesson 2 is going to be about gas pressure. What is gas pressure? Tools of measuring pressure, vapor pressure, understanding table H.
So atmospheric pressure. Atmospheric pressure is the weight of the air, and the weight of the air at higher altitudes is going to be pretty light. If you look over at our diagram on the right-hand side, you'll notice that the air molecules, the further up you go, become more and more spaced out. This is one of the reasons why when you climb Mount Everest or you go inside of a plane at very high altitudes, or you want to go in a hot air balloon, you may need to have oxygen masks so that way you can get enough air to your lungs, because there physically is not enough air in the upper atmospheres. As you go higher, the air thins out. But as you go lower and lower and lower into the earth, the air is going to become more denser. The reason why is that there's more air above it pushing down, which we call a higher atmospheric pressure. So if you're in a low-lying area, you're going to have a high air pressure. But if you're on the top of a mountain where there's very little gas, you have a low atmospheric pressure.
So we're going to now focus on the units for pressure. The pressure that the colliding gas spheres have on the container is what we call gas pressure. Atmospheric pressure is the pressure that the air exert on the Earth's surface due to the gravity.
Let's say you're just examining a section of the Earth's atmosphere. As you notice on the left-hand side, the Earth itself has a layer of gas we call the atmosphere, and about 78% is nitrogen. The other 21% is about oxygen, and the other remaining percent is just different types of gases. They can be hydrocarbons, or they can be any sort of soot or ash or any other type of particle that can become a gas. As you go higher and higher and higher away from the ground, which we also call sea level, you're noticing on the right-hand side that the amount of gas spreads out.
That's why astronauts, when they come back to Earth, they end up having to be placed in these pressure chambers to readjust their body to pressure of the atmosphere. As you get closer to Earth, the gas pressure on your skin is going to start to feel very, very heavy. And actually, the astronaut that came back from outer space last year had said that it hurt his skin to even be just standing outside in our gas pressure.
This kite surfer is hitching a ride on a moving air mass. Our transparent atmosphere reveals itself when it starts to move. Moving air, of course, is wind. The atmosphere surrounding us is a deep ocean of air extending for kilometers above us. We know that the atmosphere is essential to life on Earth. The components of air, particularly oxygen and carbon dioxide, play a critical role in the chemistry of life. Another important aspect of air is atmospheric pressure. We live at the bottom of an ocean of air. Gravity pulls on this massive layer of gas, creating pressure. The pressure is greatest at the bottom, the Earth's surface, the level where we live. Pressure is a force per unit area. The standard SI unit of pressure is the Pascal. 1 Pascal is 1 Newton of force per square meter. You will also find PSI, or pounds per square inch, used in parts of the world, particularly America. Air pressure at sea level is 14.7 psi, or 101.3 kilopascals. That's over 101,000 newtons of force per square meter. If you have a small kitchen table, 1 meter square, the force on that area created by air pressure is approximately 101,000 newtons, equivalent to the weight of 10 cars sitting on the tabletop. If air pressure can generate such huge forces, why don't we notice it? Why doesn't the table collapse? It turns out that pressure in a fluid like air transmits in all directions, not just down. This means that the 101,000 newtons of force pushing down on the tabletop is balanced by 101,000 newtons pushing up. Forces are balanced. Similarly, our bodies are not crushed because the fluids contained within our skin exert a pressure that balances atmospheric pressure. Here is a simple demonstration that reveals the presence of atmospheric pressure. Fill a glass with water. Cut a small piece of card large enough to cover the top of the glass. Lay the card on the glass. Hold the card in place and rotate the glass full of water. Surprisingly, the water stays in the glass. Here's the explanation. The card provides a rigid membrane between the water and the air in the room. Air pressure pushes up on the card. Air pressure is not pushing down on the water because there is a vacuum at the top of the water. Air pressure is pushing on the outside of the glass, but this does not affect the water. The only downward force from the water is its weight. The upward force of air pressure easily supports the weight of the water. If we drilled a hole in the top of the glass, air pressure would push on the top of the water would fall from the glass.
So let's look at Table A. Table A is the standard temperature and pressure chart, which is otherwise known as STP. At standard temperature, we call that 273 degrees Kelvin, otherwise 0 degrees Celsius. It is the temperature at which water freezes. Pressure is given to you at 101.3 kilopascals, kPa, and it is equivalent to 1 atmosphere. On Table A, please add, next to standard pressure, that 1 atmosphere is also equal to 760 millimeters of mercury, which is mmHg, and that 1 atmosphere is equal to 760 torr. These are going to be the 4 different pressure units that we are using in the gas laws chapter.
So we can measure gases by using a Torricelli barometer. As the atmospheric pressure increases, the level of the mercury in the barometer increases.
So Mount Everest is really high in the atmosphere. And since it's really far away from the sea level, that means there's going to be less gas, which means you have a low atmospheric pressure. Therefore, the level of mercury should fall. There should be less in the column. However, if you're at the Dead Sea, which is about 1,371 feet below sea level, there should be obviously more gas because that's a low-lying area. So therefore, the pressure should be higher and the mercury in the column should be higher up than where it normally should be. This is why we use millimeters of mercury, mmHg, because most of the devices to measure gas pressure use mercury. Also, the unit torr comes from the Torricelli barometer. Again, 760 torr is equal to 760 millimeters of mercury.
Here's another device that we can use to measure pressure. It's called a manometer. It's a U-shaped tube. Basically what you do is you take the difference of the heights on both sides of the tube. One side of the tube is closed off to only a specific pressure, while the other side is completely open to the atmospheric pressure.
Manometers are commonly found inside of cars because that is your gas tank. Gasoline, once it is poured into the tank of any automobile, will sort of vaporize. That vapor puts a lot of pressure on the tank, which, using a manometer, can then determine or tell you if your car is full, is it half full, or is it close to empty. And it's all based on the pressure the gasoline gives off inside of the tank. So let's look at Table H, which is all about vapor pressure. Vapor pressure can be thought of as the degree to which the liquid molecules are escaping into the gas or vapor phase. So, let's just analyze what we say. The physical solid dark line for the 4 different substances, propanone, ethanol, water, and ethanoic acid, that solid line represents the boiling point at whatever temperature on the x-axis and vapor pressure in kilopascals on the y-axis. If you ever are above the line for the compound you're looking at, that means you are in the gas phase. If you are below the line, that means you are in the liquid phase. See that dashed line across the middle? That is standard pressure. So if you are at sea level, all of those substances, propanone, ethanol, water, and ethanoic acid, these substances will boil at the temperatures shown on the x-axis.
This is what we refer to as normal boiling point.
So vapor pressure and boiling points, these are 2 common phrases that will be talked about. Boiling occurs when the vapor pressure reaches or surpasses the surrounding pressure from the atmosphere, which means that the gas trying to be released from your liquid has more force than the gravity pushing down on your sample of liquid. So when your vapor pressure is equivalent to your atmospheric pressure, this means your sample is at what we call the boiling point. So looking on the left, bubbles cannot form since the vapor pressure is much less than atmospheric pressure, which basically means there's so much pressure being pushed down that you can only evaporate your liquid.
Now, evaporation occurs because, remember, those little particles inside the liquid are all moving at different kinetic energy rates. So some of them are moving so fast that they just escape from the liquid phase,
which we call evaporation. But on the right-hand side, when we start to do boiling, when we're applying lots of heat to our sample, it's causing them to rise in temperature, more kinetic energy, which means that they will start to vaporize, which means that the vapor pressure is more than the atmospheric pressure, and thus you get a nice rolling boil, lots of bubbles can form, and gas will be escaping into the atmosphere. So again, when we look at table H, that dashed line represents the normal boiling point for these four liquids at standard pressure, which is 1 atmosphere or 101.3 kPa. The normal boiling point is defined at which the sample will boil. So if you ever forget what the boiling point of water, ethanol, propanone, or ethanoic acid is, this chart will tell you what temperature they boil.
If you look at water at standard temperature and pressure, we always say that water boils at 100 degrees Celsius. As you go up Mount Everest, you will see that water will boil at lower temperatures. And as you go further down below sea level, then you're going to have water boil at much higher temperatures. So as you can see all the way to the left, where we're at sea level, so we're at 101.3 kilopascals, which is the standard pressure, we're below 100 degrees Celsius, which water won't boil because, as we know, the normal boiling point for water is 100 degrees Celsius. As the temperature rises, however, and gets to 100 degrees, that's when we're going to see that rolling boiling happen within the water molecules. Then, if you were to do the same scenario at the top of Mount Everest, which has a pressure of 34 kilopascals, we don't need that much heat to actually create a boiling point for water. Water does not need to boil at 100 degrees Celsius at different pressures.
So let's do some practice problems, and you're going to need your reference table H to figure them out. What is the Celsius temperature at which propanone turns into a vapor if the vapor pressure was measured to be 130 kilopascals? Find propanone, find 130 on the Y, and then figure out where they touch, and draw your finger down to the x-axis to figure out the temperature. You should have got 64 degrees Celsius. Let's also use ethanol, but now let's figure out what temperature will ethanol boil if it's at 130 kilopascals. You should have got 359 Kelvin. Remember, Kelvin is equal to Celsius plus 273. At what Celsius temperature will water turn to a vapor if the vapor pressure was measured to be 1.28 atmospheres? You may need to convert 1.28 atmospheres into kilopascals before you do this. You should have gotten 107 degrees Celsius.
Remember, you take 1.28 atmospheres, and since 1 atmosphere is equal to 101.3 kilopascals, you're going to multiply 1.28 by 101.3.
So when we talk about intermolecular forces in the vapor pressure, at a given pressure, a substance that has a high boiling point has a strong intermolecular force. So that's just like, when you look at table H, look at the thing that has got the highest boiling point. That means it has the most amount of intermolecular forces. At a given temperature, a substance that has a high vapor pressure also has a weak intermolecular force, and vice versa. So at a given temperature, anything with a low vapor pressure is going to have a very high intermolecular force.
Just to make sure we're clear, the first bullet here represents the fact that you are holding your y-axis at one pressure point. On the bottom bullet, you are holding the temperature at one temperature, and you're comparing all four of those lines.